Hello and welcome to this next lecture on pattern recognition course. We have been looking at essentially neural network models for the last few classes. We looked at feed forward networks with sigmoidal activation function as well as rail based function networks and learning algorithms for using them, and both of them are useful models for learning nonlinear classifiers and regression functions, right. Then end of last class we said that we will move on to a next approach for learning nonlinear classifiers, where instead of wanting a general parameterized class of nonlinear classifiers, we are looking at learning a linear classifier in a transformed space, right. That is the so called support vector approach. So, that is what we start with today, the support vector machine approach, right. We briefly discussed it last class. So, the basic idea is the following. You from the original feature space, you nonlinearly map the feature vectors into some other space, okay. Normally a higher dimensional space, though not necessarily so. So, you map into a different space, and in the new space learn a linear classifier. Now, this works because the linear classifier in the new space could be an appropriate nonlinear classifier in the original space. If you do the mapping properly, if you choose the right mapping, then the linear classifier in the new space would be a nice nonlinear classifier in the original space, right. As an old Bob Dylan song refrain used to have, one man's ceiling is another man's floor. So, what is linear depends on which space you are in. So, what is linear in one space could be non-linear in another space. So, we have shown an example of this last class. Let us recall it is a 2-dimensional example. Suppose the original feature space is 2-dimensional and let us say x1, x2 are the 2 feature components. Now, let us define a function, a nonlinear function that maps R2 to R5. That means, you are transforming the 2-dimensional feature space into a 5-dimensional feature space. So, it is a function phi that maps R2 to R5 given any x, the image of x phi x, which we call by z, is given by 1 x1 x2 x1 square x2 square x1 x2 is a 5 component vector, right, because it is an R5. I am sorry, it is actually 6 component vector, it should have been R6. I am sorry about it, is not R5, but is R6. Now, the main idea is that if I look at a function of x, the 2-dimensional vector x, which is a0, a1 x1, a2 x2, a3 x1 square, a4 x2 square, a5 x1 x2, then this is a quadratic discriminant function in the original 2-dimensional space, right, because it has quadratic terms in the feature components. On the other hand, if I take a function of the vector z, let us call the components of z as this is z0, z1, z2, z3, z4, z5, right. So, essentially because of this 1, it is like an augmented feature vector in R5, okay. The rest of the feature vectors are R5, but I am doing an augmentation. So, we will call this as z0, then z1, z2, z3, z4, z5. Then if I write a gz as a0 plus a1 z1 plus a2 z2 plus a3 z3 plus a4 z4 plus a5 z5, this is a linear discriminant function in the phi x space, right. So, what is linear in terms of the components of z would be non-linear in terms of the components of x, right. This is the basic idea. So, if I can find the right transformation, I can use techniques for learning linear models for learning nonlinear classifiers in the original space, okay. Of course, there are, as we mentioned, if I just naively try this idea, there are 2 major problems, right. By naively try, I mean I simply think of a function phi, transform all x's into z's, and then on use any linear method that we learnt. What is the problem? As we can see from the previous example, when I wanted quadratic, I need all quadratic terms in the in the components of z, right. So, I need x1 square, x2 square, x1, x2 and so on, right. So, essentially if I need a pth degree polynomial at the discriminant function in the original space, then in the transformed vector I should have terms that contain all pth degree terms in components of x, which means there will be order m to the power p terms in the vector z. So, z would have very huge dimension. So, even in the quadratic case, I have taken 2, but if I have got let us say a 100 dimensional vector, which is not very uncommon in pattern recognition, then I will have of the order of 100 square components in z, that is 10,000. On the other hand, if I want a cubic discriminant function up to third degree polynomial, then I would not have 10 power 4, but I would have 10 power 6 components in z, a billion components in z, instead of being 100 components in z. So, the dimension of z can be very huge, even for second and third degree polynomial discriminant functions that we may want to learn. They are not particularly nonlinear, just quadratic or cubic functions in the original feature space. The transform space can have huge dimension, and this can result in huge computational costs. Let us say what do you have to do when to classify? I have to calculate W transpose x, right. If x is a feature vector for any linear classifier, I essentially calculate something like W transpose x. In the original space, it will mean only 100 multiplications if it is a 100 dimensional space, but if you are learning a cubic classifier, a cubic discriminant function, it will be a million component z. So, it will mean a million multiplication. Every time I do a simple W transpose x operation is a million multiplications, right. So, learning the classifier as well as the final operation of the classifier can be very costly, right. Now, during learning I might have to store let us say 1000 100 dimensional vectors. Instead of that, now to store 1000 million dimensional vector, right. That's a a 10,000 fold increase in the memory needed. So, it incurs large computational costs. Not only that, to learn the linear classifier in this new space, I have to learn order m power p parameters, right. W will be the same order as the feature vector. So, if I am learning a linear classifier in the z space, the W in that linear classifier should have the same dimension as the vector z. So, that means I have to learn order m power p parameters if I am learning a p degree polynomial in the original space. If I am learning a linear in the original space, I will learn only order m. That is, instead of learning 100 parameters for a hyperplane in the 100 dimensional feature space, I am learning a million parameters, because now my feature space has become a million dimensional. Now, to learn 100 parameters based on our VC dimension hyperplanes, VC dimension of hyperplanes is of the order of the dimension of the space is actually dimension of the space plus 1. So, in the 100 dimensional space, the family of hyperplanes will have VC dimension 100. So, maybe I need 1000 examples. Here, because the space has dimension 1 million, I may need 10 million examples. 10 million examples are huge, we can't get them. Even getting 1000 examples may be difficult, but 10 million examples is much more difficult. Right. Now, this is also an extra problem. So, basically both in terms of computation and in terms of being able to learn well with the available examples, this naive idea will not work. So, the nice thing about what we call support vector machines is that they offer an elegant solution for both these problems. Okay. So, let us look at what these are. They essentially learn not any hyperplane, but what we term optimal hyperplane. Okay. An optimal hyperplane is a separating hyperplane that maximizes the separation between classes. We will formally define it in a couple of minutes. Now, learning optimal hyperplane is essentially what allows SVMs to learn well with fewer examples, even in a very large dimensional space. Then they only effectively map the original feature vectors into a high dimensional space. Of course, they learn a nonlinear discriminant function by learning a linear classifier in a high dimensional space, but this is done using what is known as a kernel function, whereby we never actually explicitly do this mapping. We never calculate phi of x, we never work in the range space of phi. We shall see why, how it is feasible. By using kernel functions, we never actually explicitly calculate this mapping, right. So, we only effectively find a linear classifier in the high dimensional space. So, ultimately as it turns out, for the sake of solving a quadratic optimization problem, we will look at the dimension of the quadratic optimization. It turns out to be dimension of the number of examples rather than the dimension of the feature vector, but we solve only a quadratic optimization problem and are able to do this mapping into a high dimensional space and landing a linear classifier there. Okay. So, with that introduction, let us move on to formulating the SVM method. First, we will look at formulating it for the linearly separable case, and then we will look at the more general case. Okay. So, this is the training set given to us. We will revert back to our old training set notation. Remember, when we are considering all linear models, we are using x's for feature vectors or and y's for targets or classes, and small n as the number of examples. So, earlier when we consider neural networks, because y's happen to be outputs of the network nodes, we used di as the desired output in the training set. Now that we do not have that problem, we will revert back to the original notation we have. So, x's are the inputs and y's are the targets or the class labels. So, we are given n examples, xi are in m dimensional input space. So, we will take m to be the dimension of the feature vector space, and we choose class labels for here to be plus 1 minus 1. Earlier when we consider linear classifiers, we mostly chosen 0 and 1 as the 2 class labels, but we will take plus 1 and minus 1. We are only going to look at 2 class problem. Okay. Multi-class will be solved much like in the linear models by using one of the many techniques that we discussed there. So, we will consider only the 2 class problem. The 2 class will be taken as plus 1 minus 1. To start with, we are assuming that the training set is linearly separable. That means, there is a weight vector w belonging to Rm and a constant b belonging to R, such that whenever yi is plus 1, that means xi belongs to the class plus 1, w transpose xi plus b is greater than 0, and whenever yi is minus 1, we have w transpose xi plus b less than 0. So, all class 1 patterns w transpose xi plus b greater than 0, all class minus 1 patterns w transpose xi plus b less than 0. Because there are only finitely many patterns, if they are separable, they will be exactly separable, right. So, no pattern need be on the separating hyperplane. So, we will take both inequalities to be strict. Now, of course, we know we have already seen when we consider perceptron that such a thing is called a separating hyperplane. So, w transpose x plus b is equal to 0 is the equation for a separating hyperplane. As we seen when we discuss perceptron, if there is one separating hyperplane, if the training data is linearly separable, then there are infinitely many separating hyperplanes, right. So, the question comes, which is a good separating hyperplane? Earlier, say for example, when we did perceptron, all we were bothered is about finding any separating hyperplane. That is all we actually proved about perceptron, that it can find a separating hyperplane. But because we know there exists infinitely many separating hyperplanes, can we say that some hyperplanes are better than others? So, here is one way of looking at it. Look at that dark line in the center. For now, forget about the 2 faint lines on either side. Let us say for this problem, we would like to say that this is a good separating hyperplane, whereas this is not so good. Why do we say, why do we want to say that? Essentially, looking at the spread, the classes seem to be spread like this. So, this line seem to exactly bisect the main line along which classes are spread, right. But that is intuitive, that is more difficult to capture. But another way of seeing it is, you can see the nearest patterns on either side of the hyperplane are so far apart for this hyperplane, whereas for this hyperplane, the nearest patterns are much closer to the hyperplane. So, this hyperplane is making more commitment about unseen parts of the space compared to this hyperplane. This hyperplane is keeping itself as far away from both side patterns as possible, and hence getting lot of what I may call margin of separation, what we will actually ultimately call margin of separation, right. So, on either side of the hyperplane that I am finding, the patterns are sufficiently far away, and that gives me some intuitive feel that this might be a better hyperplane. Okay. So, this is essentially what is one intuitive way of thinking good hyperplane. It turns out even more formal is a good separating hyperplane. If the closest pattern to the hyperplane on either side is far away for one hyperplane, then that hyperplane is better than another hyperplane for which it is closer, because here it is too close. So, this is not as good a separating hyperplane as that one. Okay. So, let us now try to formalize this notion that the closest pattern should be far away. Recall that the training set is linearly separable and hence we have this WB. Now, because the training set is finite and for each of the class plus 1 patterns strictly greater than 0, each of the class minus 1 patterns strictly less than 0. So, if I take minimum of this over all class 1 patterns, it will be some epsilon 1 which is greater than 0 strictly. If you take maximum of this over all class minus 1 patterns, it will be some minus epsilon 2, where epsilon 2 is positive. And if I take smaller the epsilon 1, epsilon 2 is epsilons, I can always satisfy W transpose xi plus b is greater than or equal to epsilon if xi is class plus 1, less than or equal to minus epsilon if it is minus 1. Because there are only finitely many patterns, and if they all, or if W transpose xi plus b is positive for all of them, there must be a smallest number for it. We are calling that epsilon 1. Similarly, the largest number for this, we are calling that minus epsilon 2, and then we are taking small of epsilon 1 or epsilon 2, so that we can satisfy this. Once we can satisfy this, now I can now divide this entire equation by epsilon, because it is a positive number, right. Dividing the inequality by epsilon simply means I am scaling W on B. Now, if W transpose x plus b is equal to 0 as separating hyperplane, then KW transpose x plus KB is also a separating hyperplane. So, KW plus KB will also be a separating hyperplane. So, I can scale the W on B to satisfy W transpose xi plus b is greater than plus 1 if xi is in class plus 1, is less than minus 1 if xi is in class minus 1. What does this mean? Now, we can rewrite this as, because y which is chosen to be plus 1 minus 1, I can write both these inequalities together compactly as yi into W transpose xi plus b is greater than or equal to 1. Actually, to be able to write like this and hence simplify our algebra is why we have taken yi to be plus 1 minus 1 in this case. So, we can always scale any separating hyperplane, so that it will satisfy yi into W transpose xi plus b is greater than or equal to 1. Okay. So, what does it mean? When training set is separable, any separating hyperplane WB can be scaled, that is, we can always take a WB to satisfy yi into W transpose xi plus b greater than or equal to 1. What does that mean? If xi is class plus 1, then W transpose xi plus b is greater than plus 1. If it is class minus 1, W transpose xi plus b is less than minus 1, which means for no training pattern, W transpose xi plus b is between plus 1 and minus 1, which is same as saying there is no training pattern between the two parallel hyperplanes W transpose x plus b is equal to plus 1, W transpose x plus b is equal to minus 1. W transpose x plus b is equal to 0 is my hyperplane, but for all class 1 patterns W transpose x plus b is greater than 1, greater than or equal to 1. All class minus 1 patterns W transpose x plus b is less than or equal to minus 1, which means if I take the two parallel hyperplanes W transpose x plus b is equal to plus 1 and W transpose x plus b is equal to minus 1, there will be no training pattern between them. Now, the distance between these two hyperplanes will be 2 by norm W. Norm W is W transpose W square, norm W square is W transpose W. This is a simple coordinate geometry problem, I am sure you can easily do this. So, let us look at what this means. See, this is the W transpose x plus b is equal to 0 hyperplane. So, W transpose x is equal to plus 1 and minus 1 are on either side of this hyperplane, right, because they will be parallel, they will be just the hyperplane moved parallel to itself on either side. So, this one will be W transpose x plus b is equal to plus 1, other will be W transpose x is equal to minus 1. What I showed as M here, that is the margin, right. Simple coordinate geometry will show you that this margin is 2 by norm W, right. Okay. So, actually W is, as you know, a hyperplane, because hyperplane equation is W transpose x plus b is equal to 0, W is a normal vector to the hyperplane, right. So, that is why how we shown the W there. Because the distance between the two hyperplanes is 2 by W, distance between the hyperplane and the closest pattern is 1 by W. Because we are only guaranteeing that between W transpose x plus b is equal to plus 1 and is equal to minus 1, I will not be able to, there will not be any training pattern. I mean, so saying WB can be scaled up to this, can't be scaled beyond this. If I scale beyond this, it will go. So, ultimately the closest patterns will be either on W transpose X plus B is equal to plus 1 or W transpose X plus B is equal to minus 1 as in this figure. So, if I take this orientation for the hyperplane, right, then this is the separation I can get. So, this will be symmetric on either side. Okay. So, the distance between hyperplane and the closest pattern will be 1 by instead of 2 by norm W, it will be 1 by norm. See, in general, because both sides the patterns need not have to be symmetric, one side patterns may not actually be on this hyperplane. By the time I move this hyperplane this much, I may have hit these patterns. On this side the patterns may be far away, but I can't hit any more because these two hyperplanes have to be W transpose X plus B is equal to plus 1 and W transpose X plus B is equal to minus 1. So, ultimately, if margin is 2 by W, I know at a distance 1 by norm W, there is a pattern and no pattern is closer than 1 by norm W, right. So, distance between the hyperplane and the closest pattern is 1 by norm W. Intuitively, more the margin, better the chance of correct classification of new patterns, right. If the margin is more, I am leaving much more space for me for some more patterns to come here. So, given that these are IID examples, very unlikely that a pattern from this class comes this side. So, more the margin, intuitively better is my hyperplane. So, essentially you want a hyperplane that has maximum margin. So, we will define optimal hyperplane to be a separating hyperplane with maximum margin. So, we want to find a separating hyperplane W comma B for which 1 by norm W is maximum or norm W is minimum or norm W square is minimum or W transpose W is minimum, right. I want to maximize margin. So, I have to maximize 1 by norm W, which is same as minimizing norm W, or which is same as minimizing norm W square. So, I essentially want a separating hyperplane for which the margin is maximum or W transpose W is minimum. Okay. Okay. So, let us formulate this. Among all separating hyperplanes, the one with the largest margin is the optimal hyperplane. Okay. So, we can now write this as an optimization problem. What is the optimization? As we have seen, we want something that has a separating hyperplane that has least margin, that is maximum margin or least W transpose W. So, finding an optimal hyperplane is same as finding a W on B, W belong to Rm and B belong to R, to minimize W transpose W, subject to the constraint that these W on B form a separating hyperplane. For them to form a separating hyperplane, they have to satisfy yi into W transpose xi plus b greater than or equal to 1. I is the index of the example, so I goes from 1 to n. So, for each example xi, yi into W, each example xi yi into W transpose xi plus b should be greater than or equal to 1. This tells me that the hyperplane given by W on B correctly separates. Correctly, I mean no pattern in between W transpose xi plus W transpose x plus b is equal to plus 1 and minus 1. Among all such WB which satisfy this, I want that one which has the least W transpose W or maximum margin, right. Such things are called constrained optimization problems, right. We want to minimize this, but do not want to minimize this over all W on B, but only over those W on B which also satisfy this. So, among all WB that satisfy these constraints, which is the one that minimizes this, right. Such optimization problems are called constrained optimization problem. These are unlike the optimization we have come across so far, where when we are minimizing empirical risk, it is just some function to minimize. It is like finding maximum or minimum of a high dimensional function. With just a function f of x, you are asking which x will minimize this among all x in the space. Is now no longer that. Right. Among all x that satisfy some constraints, which one will minimize this function? Such things are called constraint optimization problems, and since some of you may not have done constraint optimization earlier, I will give you a very brief review of constraint optimization. So, any general constraint optimization problem is of the following kind: minimize some function f of x subject to some constraints. We are only interested in what are called linear constraints, so we will take them to be linear constraint. So, minimize f of x subject to aj transpose x plus bj less than or equal to 0, j is equal to 1 to r. So, I have or constraints. A1 transpose x plus B1 should be less than 0, A2 transpose x plus B2 should be less than or equal to 0, and so on and so forth. F is a function that maps Rm to R, and we assume it to be continuously differentiable. These Aj vectors are also in R because I want to calculate Aj transpose x. So, this is some linear function of x, affine function of x. Okay. Normally, you call this at the objective function or cost function or criterion function. So, you want to minimize the cost or a criterion function or objective function subject to these are called the constraints, right. So, what it means is search only among those x in Rm which satisfy all these constraints, and among all those x find the x that minimizes f. Okay. That is the problem. Such a problem is called a constraint optimization problem. Okay. See, in general, in an unconstrained optimization problem I have no constraints. So, I am just finding an x or Rm that locally minimizes f or globally minimizes f. A simplest way of looking at it, sometimes there might be a solution for a constraint optimization problem, but there will be no solution to unconstrained optimization. Suppose I want to minimize 3x. Now, there is no minimum. You can take x as low as you want and I keep going down. So, ultimately I hit minus infinity, right. This. On the other hand, suppose I want to minimize 3x subject to x greater than 0, then obviously the minimum is 0, minimum exists, right. So, essentially that is what is meant by when I want to minimize 3x, I have to search over all possible x. So, I have no minimum, but when I say subject minimize 3x subject to x greater than 0, I need to only search over those x which satisfy my constraints. Okay. A point x in Rm which satisfies all the constraints is called a feasible point, right. So, given this constraint optimization problem, any x that satisfies the constraints is called a feasible point. So, any x that satisfies Aj transpose x plus Bj less than or equal to 0, j is equal to 1 to R, all the constraints have to be satisfied, then it is called a feasible point. So, essentially we are going to minimize f or those x that are feasible. Okay. Now, we can define what is the solution. Any x star in Rm is called a local minimum of this problem or local solution to this problem if f x star is less than f x for all x that is feasible and is in a small neighborhood of x star. For an unconstrained problem, we define x star to be a local minimum if f x star is less than f x for all x in a neighborhood around x star. Now, I want f x star to be less than f x for all x in a neighborhood around x star, but not every x in the neighborhood need to satisfy this. Only all feasible x in a small neighborhood around x star need to satisfy this. Similarly, for a global solution, I want this to be satisfied by all x in Rm, but only those x which are feasible. So, normally with unconstrained minimization, x star is a global minimum if f x star is less than f x for all x in Rm. Now, for the constraint problem, it is a global minimum if f x star is less than f x for any x in Rm that is feasible. X in Rm that are not feasible do not have to satisfy this, right. That is essentially what a constraint optimization problem is. Unlike an unconstrained optimization, here we need to minimize only over the feasible set. Okay. Now, how does one solve this? No unconstrained optimization problem, we can differentiate and equate to 0, that is what we have been doing, right. The gradient descent is a simple method to solve the unconstrained optimization problem. How do we solve the constraint optimization problem? Now, for our case, we need to for the SVM algorithm that we are going to discuss, we need to look at only constraint optimization problems whose constraints are linear and whose cost function or criterion function is convex. So, we will restrict ourselves to only convex functions, just in case some of you do not know what a convex function is. A function f Rm to R is said to be convex if for every x1 x2 in Rm and all real numbers alpha in the open interval 0 1, that is at alpha strictly between 0 and 1, f of course, it can even be closed interval 0 1, but it does not matter. F of alpha x1 plus 1 minus alpha x2 is less than or equal to alpha times f x1 plus 1 minus alpha times f x2. Geometrically, what this means is, if I look at the graph of f x, right, let us say f is R2 or function of Rm to R. If I look at the graph of f, and if I take 2 points x1 x2 and I join them on the graph, then the actual graph should be below the line that joins. But anyway, this is the condition for convexity. For example, x transpose x is a convex function, you can easily verify this. When f is convex, the reason why convexity helps is in the optimization problem every local minimum is also a global minimum. You do not have to worry about local minimum problems. When f is convex and the constraints are linear, in that case in the optimization problem every local minimum is also a global minimum. That is a huge advantage when solving an optimization problem. Okay. Now, how do I solve this constraint optimization problem? Given the optimization problem, we define a function L. L is a function of your x is an m vector and also a vector mu. Mu has as many components as their constraints, they are all constraints. So, this vector mu is mu1, mu2, mu1. Yeah, just a small notational comment. Just for the optimization tutorial, so to say, we will use the notation that all bold figures are x. See, so far we have not been distinguishing between vectors and scalars, but just for this optimization part, just these 3-4 slides where I discuss optimization, I will use all bold face characters for vectors. So, these x's are vectors, aj's are vectors, but bj's are scalars, okay. Just so that it is a little more easier. When we revert back to our pattern recognition, of course, there we know capital X is a feature vector, capital W is your weight vector and so on. So, there we do not use any notation like earlier, which are vectors as scalars is clear from context, because this is an abstract optimization problem. I decided to use bold face for all vectors, okay. So, you will see throughout as long as I am discussing this abstract optimization problem. So, this mu is another vector, it has r components mu1, mu2, mu r. So, we define a function L, a function of x and mu as f of x, my criterion function, plus j is equal to 1 to r, where r is the number of constraints, mu j times a j transpose x plus b j. I am writing all my constraints as what are called inequality constraints. My constraints are all of the form a j transpose x plus b j less than or equal to 0. Okay. So, the L function I am writing is f of x plus some mu j times a j transpose x plus b j summed over j is equal to 1 to r. Okay. Such a L is called the Lagrangian for the problem, and these mu j's are called the Lagrange multipliers. So, the Lagrangian essentially adds the criterion function to some unspecified constant times the constraint. Okay. And the nice thing about this Lagrange method is that it essentially transforms the constraint optimization problem into one of unconstrained optimization of the function L in a specific sense. Okay. Let us look at the specific sense. So, we are considering the whole optimization problem, that is minimize f subject to linear constraints a j transpose x plus b j less than or equal to 0, we are assuming f is convex. Now, here is the theorem that is of interest to us. Any x star is a global minimum if and only if x star is feasible, then the x star satisfies all the constraints, and there exists some constants mu j star or such constants which satisfy the following. One is that the gradient with respect to x, the first component, the first vector variable of the Lagrangian. Lagrangian is a function of x and the Lagrange multipliers mu. So, the gradient of L with respect to the optimization variables x evaluated x star mu star is 0. 2, all the mu j stars are non-negative, and 3, mu j star into a j transpose x star plus b j star is equal to 0. Now, we know mu j star is to be greater than or equal to 0. So, if mu j star is equal to 0, then anyway this is 0, but if mu j star is strictly greater than 0, then a j transpose x star plus b j has to be 0. I know because x star is feasible, a j transpose x star plus b j less than or equal to 0. It may be equal to 0 or it may be strictly less than 0. What the third constraint says is it cannot be strictly less than 0 if mu j star is greater than 0. If mu j star is greater than 0, the constraint has to be satisfied by equality. This third condition is often known as a complementary slackness condition. So, whenever the Lagrange multipliers mu j star are positive, then the corresponding constraint has to be satisfied by equality, right. So, these are called Kuhn-Tucker conditions. So, given this optimization problem where the cost function is convex and the constraints are linear, these are the conditions for any x star to be a global minimum. What are the conditions? X star should be feasible and there must exist Lagrange multipliers mu j star such that gradient with respect to x of L of x star mu star is equal to 0, all the mu j stars are positive, and if any mu j star is strictly greater than 0, then A j transpose the corresponding for that j, A j transpose x star plus B j should be equal to 0, right. This is called the complementary slackness. Essentially, because we know all the AJs and BJs and we can F is given to us, I can calculate L, I can actually find the gradient of L equated to 0 and then make some guesses about which of the constraints are active, which are inactive, right. Active meaning when is JJ transpose x star plus BJ equal to 0, when is strictly less than 0, right. So, I make guesses about which mu j's are 0, which if I decide these mu j's are 0, right, then for the remaining mu j's I have the extra for remaining indices j, I have extra equations AJ transpose x star plus BJ is equal to 0. So, I can solve AJ transpose x plus BJ is equal to 0 and this gradient equal to 0 equation together to obtain all the mu j's and the x's, okay. So, there is a way of solving the constraint optimization problem by finding an x star which satisfies these Kuhn-Tucker conditions. There are many other methods, there are just like gradient descent, there are other numerical techniques for solving this, but we will look at one particular technique which is used for the support vector machines, which is solving it using the so called dual of the problem. Duality is a very important and deep concept in optimization. Once again, in this course we will not be able to teach duality, but those of you who may not have gone through an optimization course will just look at duality in the very limited context, right. We will just look at one way of formulating another optimization problem, which we will call the dual of this optimization problem. But even that method will work only for optimization problems where the cost function is convex and the constraints are linear, okay. So, only for that case we will look at how to find duals, okay. So, the given optimization problem is, to recall, minimize f of x subject to AJ transpose x plus BJ less than or equal to 0, where assuming f is continuously differentiable and also convex now, and AJs are vectors in Rm. So, this is okay, we are given R such constraints, and this given optimization problem is called the primal problem. In this optimization problem, the minimization is over x, right, x is in Rm. So, the optimization variables are x belonging to Rm, this is what you are minimizing over. So, the dimensionality of this optimization problem is m, you are searching over Rm to find the minimum, okay. So, now, this is the Lagrangian for x in Rm and mu in Rr, this small r is the number of constraints we have, L of x mu is f x plus summation j is equal to 1 to r mu j AJ transpose x plus Bj. Given the Lagrangian, let us define a function q which we call the dual function, which maps r dimensional real vectors where r is the number of constraints to not real line, slightly extended real line, minus infinity to infinity, minus infinity included, infinity not included. In real line, even minus infinity is not included, it will just allow the q function to sometimes take minus infinity also as values, where q is defined. Now, q's domain is R, so q is defined on vectors of the type mu. So, q mu is taken to be infimum over all x in Rm of Lx mu, where Lx mu is this. So, given any mu in Rr, I define the value of q mu to be the infimum or minimum over all possible x of L x comma mu. the difference between infimum and minimum is minimum has to be attained. So, infimum is the greatest lower bound. We are asking as x goes over all possible vectors in Rm, and if I take these numbers L x mu, what is the greatest lower bound of this? So, sometimes that is a number that is actually at the value of L x mu for a particular x, sometimes it may be a limit. Okay. Because it can be a limit, sometimes the infimum may not be attained. Suppose L x mu just happens to be minus b times x, right, or summation xi, b times summation xi, or suppose is equal to x 1. Just like minimizing 3x, there will be no minimum, right. This kind of infimum may not be attained, right. So, if this is linear in any component of x, if there is a linear term in any component of x, then infimum will be minus infinity. That is the reason we allowed q to take minus infinity as one of the possible values. That if a particular mu, the infimum is not attained, then q mu would take value minus infinity. Just to allow that, we define q to be a function from RR to this rather than RR to R. Because we defined it as infimum, we have to allow the possibility that for some mu, q mu may take value minus infinity. Now, so you give me this primal optimization problem. I know f, I know aj, bj, so I can calculate my Lagrangian. Once I can calculate my Lagrangian, for every single mu, I can calculate q mu. So, I know the function q mu. So, now I formulate another optimization problem, maximize this term q mu subject to all the mu's greater than or equal to 0. This is also a constraint optimization problem. What are the optimization variables here? Is mu's. So, here optimization is over R, where little r is the number of constraints we had in the primal. So, here optimization is over R and the optimization variables are mu. This problem is called the dual to the other problem, right. So, given this optimization problem, right, using these f1 aj's and bj's, I formulate the L, then I formulate the Q, then I formulate a new optimization problem, which is also a constraint optimization problem over RR with mu as the optimization variables, and this problem is called the dual to the primal problem. And there are some very nice connections between the primal and the dual problems. What are the connections? If the primal problem has a solution, then dual also has a solution and the two optimal values are same. What does that mean? This is the primal problem. X star could be a solution, then if the solution satisfies the Kuhn-Tucker conditions, and the optimal value is f of x star here, right. This is the dual problem. If a solution exists, of course, this will have its own Kuhn-Tucker conditions with respect to the optimization variables mu. If it has a solution, it could be mu star and the optimal value will be q mu star. What the theorem says is that if the primal has a solution x star, then there will also be a mu star, which is the solution of the dual, and f of x star will be equal to q of mu star. The optimal values are equal. 2, for x star to be an optimal solution for the primal and mu star to be an optimal for the dual, these are the necessary and sufficient conditions. X star is optimal for primal and mu star is optimal for dual, if and only if the two conditions are satisfied. One is x star is feasible for primal and mu star is feasible for the dual, obviously it has to be. The second condition is f of x star should be equal to L of x star mu star, should be equal to min over x of L of x mu star. Yeah. While the proof is a little complicated, we can at least see where the condition comes from. Now, essentially f of x star is equal to L of x star mu star. What does this condition mean? If f of x star should be equal to L of x star mu star, at x star mu star this term should be 0, right. Because of feasibility, all mu's are of the same sign, aj transpose x plus bj are of the same sign, so nothing can cancel. So, the only way f of x star should be equal to L of x star mu star is if each term here is 0, mu j star into aj transpose x star plus bj is equal to 0, which is my complementary slackness condition, right. Similarly, if I say f of x star is equal to minimum over x L of x mu star, that means q mu star, right, will be L of x star mu star, which will be equal to f of x star. Right. So, at least we can see why these conditions are interesting. So, this is the primal-dual relationship. The primal has a solution, so does the dual, and the optimal are equal. For x star to be optimal for the primal and mu star to be optimal for the dual, x star should be feasible for the primal, mu star is feasible for the dual, and f of x star should be equal to L of x star, mu star should be equal to minimum over x L of x mu star. We will be using the dual formulation for the SVM. Okay. Now, let us get back to the SVM optimization problem. The optimal hyperplane is the solution of what this constraint optimal problem. This is the primal problem. Minimize often W transport W. I have written now this in my standard form. I am writing my constraints as less than or equal to 0. So, I wrote it as 1 minus y a into W transpose x a plus b less than or equal to 0. There are n constraints because there are n examples, right. The W has the same dimension as the vector x, which is m. So, I want to minimize of W transpose W, which is a convex function. So, my what I call f in the abstract optimization problem is this, which is convex, and these are linear constraints. 1 minus y into W transpose x a plus b less than or equal to 0. There are n constraints. This is a quadratic cost function, quadratic function is a convex function, linear constraints, and hence Kuhn-Tucker conditions are necessary and sufficient, every local minimum is a global minimum. So, essentially to appreciate what this means is what we are asking for is minimization of W transpose W, which is same as maximization of the margin. So, if you have a general thing, margin is essentially you put your hyperplane somewhere in the center, right. So, on either side of hyperplane you try to make a margin till you hit one of the patterns. So, in this direction I get so much margin. On the other hand, if I change my direction, there is only so much margin possible. Right. So, this is a way of looking at what optimality means in terms of maximizing margin, right. Hyperplane in this direction has low margin, as hyperplane in this direction has high margin. So, I am trying to find that separating hyperplane which has the higher margin. Okay. Now, by the by, there are something written as support vectors here. Do not worry about this, we will come back to this figure again and then I will explain the support vectors. Okay. So, this is my optimization problem, this is f x and these are my constraints. So, my Lagrangian will be my optimization variables are w and b, mu's will be my Lagrange multipliers, this is the f x, this is the cost function, these are the constraints mu I times 1 minus y into W transpose x I plus b, this is my Lagrangian. So, if I now apply my Kuhn-Tucker conditions, what do the Kuhn-Tucker conditions give? First is that the gradient of L with respect to the optimization variable should be 0, that is gradient with respect to W should be 0 and derivative with respect to partial derivative with respect to B should be 0. If I first take gradient with respect to W of L, this term will give me a W, just so that this term will not give me 2W, but W I put a half here. Right. From this term there is only one W term here, that is mu I y I W transpose x I. So, gradient of that with respect to W will be mu I y I x I, right. That will come with a minus term. So, if I equate it to 0, I get W, the optimal W is summation over I is equal to 1 to n mu I star y I x I, right. So, if by equating gradient of L with respect to 0, I get W star as summation I is equal to 1 to n mu I star y I x I. If I equate derivative with respect to B to 0, there is only one term here that gives me B, that will be mu I y I b, summation I is equal to 1 to n mu I y I b, derivative of that with respect to b will be summation mu I y I. So, at optimal Lagrange multipliers, summation I equal 1 to n mu I star y I should be equal to 0, right. Then Kuhn-Tucker conditions also demand feasibility. So, for feasibility I need to have 1 minus y I into W transpose x I plus b star should be less than or equal to 0 for all I, and I need complementary slackness. So, mu I star into 1 minus into the constraints 1 minus y I into w transpose x I w star transpose x I plus b star should be equal to 0 and all mu I should be greater than or equal to 0. These are my Kuhn-Tucker conditions. Okay. So, w star is given by mu I star y I x I and this is my complementary slackness condition. Let us say this define the set of indices I for which mu the corresponding Lagrange multipliers are strictly positive by the set S. By complementary slackness, what does complementary slackness give me? Mu I star into 1 minus y I into x I transpose w star plus b star equal to 0. So, for any I, if mu I star is strictly greater than 0, then 1 minus y I into x I transpose w star plus b star should be equal to 0. Now, for every I in the set S, mu I star is strictly greater than 0, that is the definition of the set S. So, I belongs to S implies mu I star is greater than 0 and hence y I 1 minus y I into that is equal to 0, which is same as y I into x I transpose w star plus b star is equal to 1. What does that mean? X I transpose w star plus b star is equal to y I. By multiplying y I both sides by y I, note that y I is either plus 1 or minus 1. So, y I square is always 1. It essentially means x I transpose w star plus b star is plus 1 if x I is in the plus 1 class, minus 1 if x I is in the minus 1 class. So, actually x I is on the hyperplane x I transpose w star plus b star is equal to plus 1 or minus 1, which means if mu I star is greater than 0, then the corresponding I x I is closest to the separating hyperplane. So, we call x I where I belongs to the set S as support vectors. So, there are as many constraints as there are training examples. So, corresponding to each x I there is a constraint and hence corresponding to each x I there is a Lagrange multiplier mu I, because there are as many Lagrange multipliers as their constraints. So, we can actually say each Lagrange multiplier is for one example. So, if the Lagrange multiplier is strictly greater than 0, the corresponding example, a corresponding x I is the one closest to the separating hyperplane and these are called the support vectors. And w star we know is summation over I mu I star y I x I. If mu I star is equal to 0 anyway, that term does not contribute. So, I can actually take w star to be summation over I belonging to S mu I star y I x I, which means the optimal w is a linear combination of the support vectors. Of course, when we did perceptron, we knew that essentially a separating hyperplane will be a linear combination of the x I of the examples, but we know that the optimal hyperplane now is a specific linear combination of only some of the examples, not all the examples. These examples are called the support vectors and those happen to be the ones closest to the hyperplane. Okay. As a matter of fact, support vectors constitute a very useful output of this method apart from the w star. Identifying which of the examples that are closest to the separating class separating boundary is also a useful byproduct of the SVM method. Now, because these x's are called the support vectors and the optimal hyperplane can be written as a linear combination of the support vectors, right, the method is called a support vector machine. Okay. Let us just take a look at it now. So, this is if this is my optimal hyperplane, right. So, these the ones which are dark here, right, these two and these two of class 2 and these two of class 1 patterns, they happen to be the support vectors. Okay. They are the ones closest to the separating hyperplane. Okay. So, let us sum it up. The optimal hyperplane w star b star is given by w star is summation over I mu I y I x I, which is same as I belong to S mu I star y I x I, where S is the set of all indices I for which the corresponding Lagrange multipliers are strictly positive. And if I know all the Lagrange multipliers, I can also find b star, because the complementary slackness says for every j, yj into xj transpose mu star with b star into mu j star is 0. So, if there is any j such that mu j star is greater than 0, then yj into xj transpose w star plus b star should be equal to 1. If I multiply both sides by j and take this term on that side, I get b star is equal to yj minus xj transpose w star for any j such that mu j star is greater than 0. So, every j such that mu j star is greater than 0, I can do this, I will get the same value, that is what optimization theory tells me. So, if I know all the Lagrange multipliers mu's, then I can calculate both w star and b star. Okay. Thus, w star and b star determined by mu I star I is equal to 1 to n. If I know all the Lagrange multipliers, then I know the support vectors. W star is a specific linear combination of support vectors where the weights in the linear combination depend on the Lagrange multipliers, and B star can also be given in terms of the W star. So, we can obtain the we can now solve the dual of the automation problem to get mu stars. Okay. So, for this problem, what is my dual function? Q mu is infimum over W b of my Lagrangian is of W transpose W plus this all the constant mu I into this. Now, if I look into this, I have a mu I y I b, right, summation I is equal to 1 to n mu I y I whole into b is 1 term minus. Now, I am taking infimum both respect to W and b. So, as you already know, it is like minimizing 3x, right, is some b into some summation I is equal to 1 to n mu I. So, if summation mu I y I is not equal to 0, then q mu is equal to minus infinity, because the infimum will be only minus infinity, which means ultimately because I want to maximize q, there is no, I need to only look at those mu for which mu I y I is equal to 0. Now, how do I get infimum with respect to W? I want to minimize this with respect to W. So, take the gradient with respect to W and equate to 0, and that we already know the solution. Infimum with respect to W is attained by taking W is equal to mu I y I x I, right. So, essentially I get my dual function by substituting W is equal to mu I y I x I and imposing mu I y I is equal to 0. Okay. So, if we did this, we will get the dual of the SVM automation problem. We will look at the details once again next class, but right now I will show you the final expression. This turns out to be the dual of the SVM automation problem, right. Once again, in terms of mu, this is a linear term, this is a quadratic term. So, it is once again a quadratic cost function, and the constraints, there are so many inequality constraints and one equality constraint, but all constraints are still linear. So, the dual is once again a quadratic is a constant automation problem with quadratic cost function linear constraints. Another very important thing for us, I will once again stress it in the next class, is that the training examples come only as inner products here, xi transpose xj. That is the only way the training examples enter into this automation problem, which happens to be very useful to us later on, we will remember it. Because this dual problem, the maximization of mu is the vector of Lagrange multipliers. There are as many Lagrange multipliers as there are constraints in the primal problem. There is one constraint per example in the primal problem. So, the automation is over Rn, where n is the number of examples irrespective of the dimension of x. No matter what the dimension of x is, this automation problem is only over n. So, this is what we will remember. So, we have introduced the automation problem for the SVM. We looked at the primal problem, and we will look at the dual problem in the next class, and then see how to generalize it to a linearly non-separable case. Thank you.